And in this session, we will be dealing with the active microwave remote sensing. And microwave segments is the segment of remote sensing which is capable of penetrating clouds, and it's independent of atmospheric conditions, so that we can use microwave remote sensing even during cloudy atmosphere, rainy season, day and night, so that especially in places like Kerala, where we are most of the time of the year covered by clouds, we will be getting images uh, for the cloud covered area, and also we will be getting seasonal images, so that we can analyze crop characteristics, land use mapping. And during floods, since it is monsoon time and cloud totally cloud cover, so flood mapping and flood delineation and all other things, only microwave data will be of use. The optical side of the remote sensing may not give cloud free data, because it's most of the area will be cloud covered. So microwave is quite important, especially in place like Kerala. So let's see some of the basics of the microwave remote sensing. And we will be covering principles of radar imaging, characteristics of radar signals, resolution of radar images, synthetic aperture radar, and principles of radar interferometry. And radar is, as we all know, it's a radio detection and ranging. And we have got the microwave signals to detect the presence of objects and its properties. So, as I've told earlier, we use the microwave segment, which can penetrate cloud, and it's time independent, and so that most of the active segments work help us in getting information, especially for flood periods and cloud covered monsoon season. So what happens is, pulses of radio waves are sent from the radar antenna towards the object, and the energy scattered back are recorded in the antenna. Not all the energy, as we all know, get reflected, but whatever energy that is reflected will get recorded at the radar platform. Difference between the pulse sent and received indicates the properties of the objects and the distance of the object. Difference in the pulse sent and received. So that helps to identify properties, and the scattering characteristics and all other things helps the properties of identify the properties of the object, and the time taken and other parameters help us to identify the height of the length of the objects, and interferometric parameters help us to identify the height of the objects and elevation details. So the radar characteristics, radio detection and ranging help us to get information of the objects in uh, most of the season, most of the time, so that problems of uh, reflected areas, or visible remote area remote sensing, or the uh, passive remote sensing in other branches, will be solved in the microwave segment. That means in the visible, infrared, and except thermal area, the problems of the cloud and other things will be solved in the microwave remote sensing, because it can penetrate cloud. Radar imaging from a moving platform help us to identify uh, objects, and it can uh, it can be on a side looking platform. That means we use side looking airborne radar systems. It looks towards its side, not in the nadir direction. It has got an angle of side angle of vision. That's why it's called slide looking airborne radar. Radar systems operated from airborne, spaceborne moving platforms, and it's called a SLAR, side looking airborne radar systems, where it looks at an angle uh, to the direction of light. So we have microwave waves, pulses transmitted or emitted to the side of the through the side of aircraft, and receives back. While it moves forward, it gets back the reflections. So radar return is recorded using antennas. So basically, it will have an antenna to get back the reflections. Each pulse has a finite duration. It sends pulses again, like the case of lidar. It sends pulses. A lot of pulses are being sent, and the pulse duration, each pulse has a finite duration. It illuminates a particular strip of land. Depends on the angle of the side looking angle, height, and the pulse duration. As the pulse duration increases, the area of coverage also increases. So it illuminates a narrow strip of land normal to the flight direction. It will be mostly normal to the flight direction or perpendicular to the flight direction. So since it is a side looking, it illuminates a part of land, a piece of land perpendicular to the flight direction on a side looking mode. So radar image is generated by using continuous strips swept as the aircraft moves in the azimuth direction. Azimuth direction is the flight direction on the ground. So where the aircraft moves along the flight direction, along the azimuth direction, it continuously scans, sends pulses, and gets information, and gets continuous coverage of the land area that is being mapped. So to have some technical terms, we will have different, you can see the picture and you can see the flight direction. You can see the azimuth direction, which is parallel to the flight direction on the ground. You can see the range direction, which is perpendicular, and the imaging is done along the range direction. And we have got two near range and far range. We have got two range information, which is the near range position and far range position. As we look to the side, you will have a near point and you will have a far point where the pulses hit on the ground, where the sensing is being done. And the radar pulses sweep across swath, and the swath area that it covers will have a near range and far range. And you can see the far range angle is called the slant angle. The slant direction or the slant angle is along the far reaching direction of the illumination direction is the slant angle. And we have a depression angle, which is an angle from the horizontal plane perpendicular to the flight direction to the near range ray, so that the pulse that is being sent to the near range and to the horizontal plane perpendicular to the flight path is the depression angle. And the angle from the nadir line to the near range line is the look angle. So look angle, depression angle, these are important terminologies which we will be using across while the calculations are being done for height measurement and all other things. So there are some basic characteristics of such as wavelength, velocity, pulse length or pulse duration, phase of the wave, and look angle, depression angle, and incident angle. We will deal in details the look angle, depression angle, and incident angle in the coming slides. So the wavelength, there are different wavelength bands in the complete spectrum of microwave range that is start ranging from few millimeters to 1 meter. So each wavelength band is denoted by a letter, and commonly used bands are Ka, X, and L. So we have Ka, K, Q, X, C, S, L, P. These are the bands that is available, and the common ones will be Ka, X, and L that is being used. So wavelength starts from 0.8 centimeter to 1.1 in the Ka band. Again, K band it's 1.1 to 1.7. Q it's Ku band it's 1.7 to 2.4. X band is 2.4 to 3.8. C is 3.8 to 7.5. S is 7.5 to 15. L is 15 to 30. And P is 30 to 100 centimeters. So we have all these 7 bands available in the microwave segment, and we will be using most of it as the technology improves. Presently, Ka and X and L bands are more predominantly being used. K, Ku, X, C, S, and all other bands will be used for different characteristics as the technology improves. And we can see some of the benefits of these bands in the coming slides, and the selection of wavelength, how it is being done, can be seen here. So characteristics of the radar signals, it's a selection of wavelength which is depending upon the objective of the analysis. What we are looking at depends upon what we are looking at, whether we are looking at penetrating the clouds, penetrating the soil. All these penetration capabilities can be achieved only with the larger wavelengths, shorter wavelengths. And as the penetrate through clouds, generally less preferred for imaging from airborne, spaceborne platforms, the smaller wavelengths, and get scattered from the surface and give more information about surface characteristics in the case of smaller wavelength. So it can be used for radar interferometry also to extract the topographic information. So larger wavelength penetrates, and smaller wavelengths get scattered so that it won't penetrate the cloud and soil. So larger wavelengths are used for penetration capabilities, and data collection of within. If it is capable of penetrating cloud, data from the earth's surface will be collected, and if it is capable of penetrating soil, soil characteristics underground will be collected. So it depends on the requirement, objective of the analysis, that we will be selecting the bandwidths. The larger wavelengths will be opted for penetration capabilities, and smaller wavelengths will be opted for studying the characteristics of the objects as it is basically the objects scatter. The smaller wavelengths which will help to identify the characteristics of the objects, and also it will be useful in identifying interferometric studies, so radar interferometry, to extract the topographic informations, heights, variations, and landslide subsidence, and all these so height-related informations can be achieved with the help of smaller wavelengths. Short wavelengths like X and C are used in radar interferometry. Interferometric applications can also be used along with polarimetry, interferometry, and all these studies will give more and more information from the radar data. So data utility of the data will be more and more enhanced with the technology as the technology improves, and we will get more and more information about the objects on the land, and also underground with its penetration capabilities. So the velocity, the characteristics of the radar signal, where the wavelength, apart from wavelength, we will be dealing with the velocity characteristic. Velocity is basically the velocity of light, which is 3 into 10 to the power of 8 meter per second. It's from the bands of the electromagnetic spectrum, so that the velocity will be the velocity of light. And pulse duration and pulse length, which is an important characteristic of microwave remote sensing, and it depends. So the pulse duration or pulse length is the duration of the pulses sent from a radar system. How much time that the pulse is being sent from a radar system. The duration of the pulses sent from a radar system, and the energy transmitted and the radar image resolution depends on the pulse length. So basically, the image resolution depends on the pulse length. So we need to fix, we need to be very careful with this parameter, that is the resolution. The resolution is a main thing that helps us to differentiate between objects. So in order to improve resolution, we need to take a lot of care in identifying the pulse duration also. So energy transmitted and the radar, so that gives then a radar image resolution better resolution characteristic in the radar image, and as the resolution is dependent on the pulse length. So amount of energy transmitted is directly proportional to the pulse length. So the more the amount of energy transmitted, the more the pulse length. So the amount of energy transmitted is directly proportional. Where the pulse length is long, larger area of ground is scanned by the single pulse. So more energy is sent, more area is covered. So it's the leading to a coarse resolution. So more energy, more pulse length, leading to more coarser resolution, and less energy sent, less pulse length. So small area coverage, better spatial resolution. So we need to have an idea of how the resolution characteristic is dependent on the amount of energy transmitted. The more energy transmitted, more area covered, coarse resolution. Low energy transmitted, low pulse length, small area covered, and the spatial resolution is more. Similarly, in the case of phase of a signal, the phase characteristic indicates the phase of the wave cycle, crest and trough. Crest and trough of this wave and the other wave, when it matches, we say they have got the same phase, they are in the same phase. And if the crest of a wave match with the trough of a wave, then the phase is different. Even if it is not exactly, crest and crest are not exactly matching, that is the phase difference between two waves. So it indicates the wave cycle. So the more and more waves are in phase will give better reflection and better information to the sensor, and brightness will be more. If the phase is, as I have told, is destructive, that is the crest matches with the trough, you will get less reflection, and the information received in the sensor will be less. So the phase of the radar return depends on the total distance traveled from the radar to the terrain and back in terms of the total wave cycles. So the phase depends on the distance traveled and back to the object and back in different total the different wave cycles. When it hits an object and returns, there will be a phase difference which is used to identify the height of the objects and all other characteristics of the object. So the phase difference is used to identify the interferometric application is used to for the interferometric application, and to identify the elevation characteristics and all. So phase of the signal is an important important parameter in the case of microwave remote sensor. And the look angle and depression angle, as we have told earlier, angle between the nadir point of interest on the ground and the point of interest on the ground. It is the angle between the nadir line and the pulse line to the nearest range. That's what you have seen in the figure, and it's also shown in the figure at the bottom, where the angle between nadir and the point of interest on the ground, and depression angle is a complementary to the look angle. So look angle is angle between the nadir line and the near slant range line, whereas in the case of depression angle is a complementary to the look angle, which is to the horizontal plane perpendicular to the flight direction and to the near slant range line. So that is the depression angle, which is a complementary angle to the look angle. And incident angle is the angle between the incident radar beam and the perpendicular or the normal to the ground line, normal to the ground. So it's the angle between incident radar beam and the line normal to the ground on which this incident radar beam is hitting. So that is the incidence angle. So look angle, depression angle, and incident angle. So look angle, as we told earlier, is the angle between the nadir line to the radar beam towards the near range, and the depression angle is a complementary angle, or the angle between the near range radar beam to the perpendicular plane along the flight line. So I think that is clear, and the resolution of the radar has got two radar data has got two resolution types, and that is azimuth resolution along the azimuth direction, and range resolution along the range direction. So two types of resolution in two direction, and the spatial resolution is controlled by pulse length, as we told earlier, and the antenna beam width. The two parameters that controls the resolution are pulse length and antenna beam width. As we have seen earlier, the pulse length increases, the coverage area is more, and coarse resolution will be there. Pulse length decreases, coverage area is less, and fine resolution you will get. And on the other hand, if you go for antenna is another parameter that influences the resolution. If you have large antenna, you will have better resolution. If you have small antenna, you will have coarse resolution. So that is the importance of antenna and pulse length in radar images. Let us see the range resolution and azimuth resolution. Here the range resolution is a resolution along the range direction. Range, we have seen the range direction, and azimuth direction. Azimuth direction is the direction parallel to the flight direction along the ground, and range direction is perpendicular to the azimuth direction. So scattered signals from the objects must be received at the antenna without any overlap. So if the signals that is scattered uh, when the pulse hits the object should reach the antenna without any overlap. If it overlaps, we will not be able to differentiate between two objects. So we have told that the pulse length is directly proportional to the resolution characteristics. So if the pulse length is more, the coverage is more. If the coverage is more, the resolution is less. That means we will not be able to resolve different objects individually. And if the pulse length is small, we will be area of coverage is small. The spatial resolution will be more. We will be able to identify each object. So in the picture given below, you can see that A and B and C are not individually resolvable because of its distance and size is within the pulse length, whereas in the case of D is away from the pulse length, or its more distance is more in the case of compared to pulse length. So D is resolvable where A and B is not resolvable. So to resolve individual items, we need to have better resolution. So the pulse length should be less. More pulse length means we will not be able to resolve objects. And the range resolution is the range resolution along the range direction, and is equal to 1/2 of the pulse length. The slant range resolution is equal to half of the pulse length. So it's pulse length by 2, that is half of the pulse length. So range resolution in the ground resolution in the range direction, that is RR equals pulse length by 2 into C by pulse length into C, velocity of the signal, by 2 cos beta, or depression angle. So pulse length into velocity of the signal by 2 cos beta, that is depression angle. So this shows that as the pulse length decreases, range resolution increases. So shorter pulse length gives better range resolution. Shorter pulses reduce the total energy transmitted and hence the signal strength. So since the energy transmitted is less, signal strength will be less. Therefore, we need to employ electronic techniques to shorten the apparent pulse length and hence improve resolution. So we need to keep an understanding that if the energy that is transmitted, if it is too small, the reflection signals you will be getting will be very meager and very less powerful, so that the sensor may not be able to sense it. So we need to get techniques to send large amount of energy and to reduce the apparent pulse, shorten the apparent pulse length, so that improve the resolution. Resolution can be improved, getting a better transmitted energy back, and the pulse length is being shortened. So electronic techniques are being used for improving range resolution. So in the case of we can say that synthetic aperture radar is a technology to improve it is the azimuth resolution that follows. So after the range resolution, let us see how the azimuth resolution is calculated, and it's basically Azimuth resolution increases with narrow radar base, directly proportional to the wavelength, inversely proportional to the antenna length. So it's directly proportional to the wavelength, and the shorter the wavelength, it will have more resolution, so that inversely proportional to the length of the antenna. So if the larger antenna, better resolution. So smaller wavelength, better resolution. Larger antenna, better resolution. So we can see that it decreases from near to far range. So azimuth resolution decreases from near range to far range. So azimuth resolution RA is equal to S cos depression angle, or beta S cos beta, into lambda by D, antenna length. And RA can be improved by using synthetic aperture radars. So larger antennas, practical limitations are there. We may not be able to set up larger antennas in the satellites. So it is a practical problem to fit larger antennas, and shorter wavelength, less energy, poor penetration capacity. If the energy is less, it is not penetrating the cloud and the soil. So penetration capability will be less in the case of less energy. So we need to have a trade-off between all these things to get better resolution and penetration capabilities and all that possibility. So if you use longer wavelength, we need to have very large antennas to have a better resolution and penetration capabilities. So antenna fitting a mechanical heavy large antenna is not possible, so we can use synthesized antennas. So synthetic aperture radars are synthesized antennas use, and synthesized antennas to improve the resolution. So let us see now what is synthetic aperture radar, or SAR. Basically the SAR uses the Doppler principle, synthesize the effect of long antennas. Long antennas, in the sense we may not be able to set mechanically long antennas, but it will synthesize long antennas by looking the same location or same position or the same object from multiple locations. The satellite will look at the same object from multiple locations, and it will be considered as a single antenna, so that the resolution of the image can be improved. So that's how it is synthesizing the size of the antenna. The synthesize the effect of long antenna, synthesize the effect of narrow beam width, and better resolution in azimuth direction. So Doppler principle is used to synthesize long antennas, synthesize narrow beam width, and better resolution in the azimuth direction. So that is why it is called a synthetic aperture radar. And as we know, the Doppler principle is the if two object and the source is moving, it's in relative motion, the frequency of the sound heard will be different that from of the source that is transmitted from the source. The sound heard will be different at the target than that is being sent from the source. So it will have more frequency if the object is near, and it will have less frequency as it is far away, if the object or the listener is far away. So that is the Doppler principle. You can see it in the figure on the right side. The shorter the wavelength, you will have more frequency, and the longer wavelengths will have long frequency. So Frequency is more when the source of the listener move close to each other, and less when they move away from each other. So we will have less frequency in the left direction and more frequency on the right direction. So that is the longer wavelength, you will have less frequency, and the shorter wavelength, you will have high frequency. So Doppler principle in SAR, as I've told earlier, works by repeated scanning of the same object or the same area from different positions. It's similar to our aerial photograph where the flight takes overlapping images. So the same area will be looked from different positions. So from different positions, so that the entire distance will be calculated as a single antenna, and the processing of the image will be done like that as a single antenna. That is the synthesized aperture. The radar returns are recorded by the same antenna at different locations along the flight track, as if they are part of a single big long antenna. Apparent motion of the target through continuous radar beams is assumed as shown in the figure. So you can see the figure, the motion of the target through continuous radar beams is assumed as shown in the figure. Means you can see here the target, the flight is moving, and the target is being sensed again and again, and this image and the long antenna is synthesized as it continuously monitor the same area from different positions. The radar returns are processed according to the Doppler frequency shift. So it's based on the Doppler frequency shift, the radar returns are being processed. So that gives better azimuth accuracy in the case of synthetic aperture radar. So the interference concept is that in the case of the Doppler case, the interference is superposition of waves traveling through same medium. If it is traveling through air, how it interferes, how the phase difference is there. There is a constructive interference and a destructive interference. If the two troughs match, if it is having the same phase, it is a constructive interference. And if the crest and trough of two different waves match, that is a destructive interference, and you will have images on the right side. A constructive interference area will have bright tone, and destructive interference area will have dark tones. The phase of the resulting signal depends on distance of the point from the source, distance between the sources, and wavelength of the signal. So phase of the resulting signal after the interference, and so that after the interference with the object and the image, the signal sent and the signal received, the phase difference will help us to identify the characteristics of the object, and the phase of the resulting signal depends on distance from the point, distance of the point from the signal, from the source. So source of the signal and the distance of the object will be a parameter that defines the characteristics of the phase, and the distance between the sources. So we are sending signals to the same object from different positions. So the distance between the source of signals will also have its impact on the phase of the resultant signal. So, and also wavelength of the signal. The wavelength of the signal, distance of the object from the source of the signal, and the distance between the sources of the signal. So these three parameters will have its impact in the phase of the resulting signal. So the principles of radar interferometry. Interferometry is as we have told earlier, is based on the phase difference. So phase difference is being calculated in the case of radar interferometry. It will have difference obtained from interferograms used, and these interferograms are used to identify the height of the objects. So principles of light interference are used to estimate the terrain height, that is the interferogram. Basically we use to identify height from the interferograms generated. So it is very similar to our aerial photographs, and the radar returns from the same object is collected from two antennas or two different positions at two different times, and the difference in phase measure at the two images obtained at two antennas or two same antenna at two different times will help us to generate interferograms. Also, it's also known as fringe map. So if we have the radar reflectance collected from two antennas or from same antenna at two different times, will help us to produce interferograms or fringe maps. These phase difference generated will be used to identify height of objects. So radar interferometry is used to identify the height of the object. So we'll be dealing with the interferometric characteristics of objects and the principles in this session. So phase difference for each point in the image is estimated from the interferogram. If the single antenna is used, we will take in the radiated or reflected images two different times at two different times. So radar reflections will be taken at two different times when a single antenna is used. So we can see here in the figure it is shown that wavelength is a known value, and the phase difference phi1 and phi2 is used to calculate delta S. That is S1, S2 is the distance of the object in the near range on the point source 1 and source 2. So S1 and S2 is equal to S1 plus delta S. So that gives, it's used to calculate delta S. So phi2 minus phi1 equals 2 pi by lambda into S1 minus S2 equals 2 pi by lambda into delta S. S1 minus S2 is delta S. So the phase difference equals 2 pi by lambda into delta S. Using the principles of trigonometry, S1 can be calculated as sin beta minus alpha equals S1 plus delta S all squared minus S1 squared by minus D squared by 2S1D. So using the trigonometric principles, S1 is calculated. S1 is related to the terrain height as follows, that H is equal to height of the object, H is equal to flying height minus S1 cos theta. S1 cos theta. So S1 cos theta will help us S1 cos of look angle. So H minus S1, the distance from the or distance of the object distance of the object from the source minus, height of the satellite minus distance of the object from the source into cos of look angle. So we will be able to identify height of the object from this formula, which is being used in the radar interferometry to calculate height of the objects. So let us see the types of radar interferometry that we have already explained. That is a single pass interferometry and a repeat pass interferometry. A single pass interferometry is used when we have two antennas on board in the satellite, or repeat pass interferometry is used when we have single antenna. A single antenna which sends and collect information. In the case of repeat pass interferometry, if a single pass interferometry will have two antennas which will send and receive informations. In one antenna will send information and receive, the other antenna will receive information alone. So two antennas are located at a fixed distance which is known, and the signals are transmitted only from one antenna. The energy scattered back is received in both the antennas. The repeat pass interferometry, there is only one antenna which sends and receives back the information, and the antenna is passed more than once in the area of interest. So through closely spaced orbits, very closely spaced orbits, it can get information of the same area of interest, so that the interferometric operations can be done. And in the case of active remote sensing, let us see some active microwave sensors that is being used, including radio detection and the radar, synthetic aperture radar, real aperture radar, and scatterometers. So the active sensors create their own electromagnetic energy. Active microwave segment sends their own pulses. In the passive microwave sensors, gets the microwave energy reflected from the EMR. In the sun's energy that is heating, the passive microwave sensors sends the microwave reflections from the sun's energy. Active microwave segments sends its own energy and gets back the reflection. So the transmitted from the sensor towards the terrain interacts with the terrain and backscatter, which is getting recorded. And the active and passive remote sensing, we have been dealing with this, and it is the same here in the case of microwave segment also. So radar sends information and it's being scattered, and it captures the information back. So in the radar, it's called radar backscatter. Radar backscatter is, or the power of backscatter received, it depends on the power per unit area at target. The target, how much area power has been transmitted and hitting the power, and the effective scattering area of the target. Effective scattering area of the target into spreading loss of the radiated signal into the effective receiving area of the antenna. So power per unit area of the target, effective scattering area of the target, spreading loss of the re-radiated signal, and effective receiving area of the antenna are all factors that will contribute to the power received at the antenna. So we will have to have a combination of all these positive factors to have a better power that comes to the antenna, so that you will have better image of the received from a radar. So a radar equation is as given below, where you have got the power received equals power transmitted and gain, antenna gain in direction of target, range distance from transmitter to target backscatter area of target and wavelength. So it is power received equals power transmitted into antenna gain square into backscatter area of target into wavelength square by 4 pi cubed into range distance from transmitter to target. So that is the radar equation, and based on this radar equation we will be able to calculate the power received. And once we have we will be calculating the radar backscatter coefficient or the sigma naught by the formula. It is the efficiency of the terrain to reflect radar pulse. That is the sigma, or the radar cross section. Radar cross section is the efficiency of the terrain to reflect the radar pulse, and sigma naught, the radar backscatter coefficient. It's called radar backscatter coefficient. Sigma naught is the radar cross section per unit area. Radar cross section sigma per unit area. Sigma naught is the radar backscatter coefficient, which is the radar coefficient per unit area, cross section per unit area. So we'll be calculating the sigma naught while processing the radar data, and we will be the sigma naught is useful in the process, and we need to get these values to identify to develop the image and to identify multiple scattering characteristic of the different objects. So radar backscattering depends on the roughness and dielectric constant of the objects. The two major factors that influence the radar backscatter is roughness of the object and dielectric constant. If the object is roughness is more, you will have better information, better reflection, and if the dielectric constant is high, and it also gives better information. So it depends on the characteristics of the radar: depression angle, frequency or wavelength, and polarization. In the case of target characteristics, it's the roughness and the dielectric constant. In the case of radar, the backscatter characteristic depends on the depression angle, frequency of wavelength, and polarization of the wave. So in the case of radar part, or the characteristics from the side of radar to improve backscatter is the depression angle, frequency of the wavelength, wavelength, and the polarization of the wave. So three factors that from the radar side, and two factors from the object side or the target side, that is the roughness and dielectric constant. The dielectric constant of the is the ratio of the capacitance of the material to that of a vacuum. So it is a ratio of the capacitance of the material to that of the vacuum, or the capacitance of the material to the capacitance of vacuum, also known as relative permittivity. So this is the dielectric constant, and the dielectric constant depends on the type of material as well as the moisture state. The moisture state of the object, if it is more if it is contain more water, the moisture content is high, the dielectric constant varies. So it is dielectric constant depends on the type of material as well as the moisture state. So it is analogous to the refractive index of the material. It is primary function of moisture content. It also depends on the chemical properties such as salinity. So these three parameters affects the target object characteristics can be assessed based on its dielectric constant. So dielectric constant it's directly related to the moisture content and the refractive index of the material and the chemical properties such as salinity. So dielectric constant calculation is essential to identify the type of material Uh, so you can see here, desert has got a very low dielectric content. Grasslands has high dielectric content, moderate dielectric content in the forest area, variable dielectric content in the tundra or the frozen areas. So you can see, as I've told earlier, you can see that the moisture content increases, dielectric content increases, moisture content decreases, dielectric content decreases. So it depends. So if the dielectric content is more, dielectric constant is more, it is understood that there is more water content, there moisture content in the soil. So soil moisture studies can be done with the help of radar data, and the radar frequency and backscatter depends on the wavelength characteristics. So in the case of X band with the 3 centimeter resolution, you can see backscatter is from the mostly from the canopy itself. In the case of L band with the 24 centimeter resolution wavelength, we will be able to reach the soil, penetrate the soil, and you get information from the soil. The canopy is being penetrated in the case of L band with the 24 centimeter wavelength. In the case of C band with the 6 centimeter wavelength, we get both soil and vegetation reflex backscatter. So depth of radar penetration through vegetation canopy varies directly with the wavelength characteristic. So we will have to select our wavelength depending upon the requirement. If you are going for soil penetration, soil data, soil analytics, we'll have to go for longer wavelengths. If you want to identify characteristics of the canopy, it is shorter wavelength that is better. So we will have reflection from the top of the canopy, within the canopy, and from the bottom of the canopy, surface scattering, volume scattering, and surface and volume scattering from the ground. So these are the different types of scattering that takes place in a pine forest, which can be hypothetically, and there is more interactions in between, and multiple scattering can also occur when there is large number of trees. So response, as we have seen, it's from the surface of the canopy, from volume scattering. In the case of C band, X band, and L band, we'll have different type of scattering as we have seen earlier in the case of pine forest. And let us see some radar parameters, like azimuth direction is the direction of travel of the aircraft or orbital track of satellite. That is the azimuth direction, as we have discussed this earlier also. And the range angle is the direction of radar illumination, usually perpendicular to the flight direction. And depression angle is the angle between the horizontal plane and microwave pulse. Horizontal plane and the microwave pulse. Microwave pulse, especially to the near range. Near range, that is the depression angle. Incident angle is the angle between the microwave pulse and to the horizontal, line normal to the ground surface. And the polarization is the linearly polarized microwave energy emitted or received by the sensor. And it can be HH polarization, or VV polarization, horizontal polarization, vertical polarization, horizontal and vertical polarization, vertical and horizontal polarization. So these kind of polarization can be active, and you can see here the look angle, incident angle, depression angle, and all other things that we have discussed earlier also. Azimuth direction, and also the slant range is the direction along the slant or the look angle. Ground range is the direction from the nadir point on the ground to the look angle, to the look direction, to the range direction. So that is the ground range and the slant range. Slant range is from the satellite or the aircraft uh, along the look angle. That is a slant range. And the nadir point on the ground to the slant range is the ground range. And the radar pulse length is the you can see in the figure as the pulse length, how much it depends on the individual pulse length of individual pulse that is being sent by the radar, and the area that is being illuminated at an by a single pulse can be represented as in the figure. And it is the pulse length, and the resolution depends on the pulse length. The as we have told earlier. And the synthetic aperture radar, as we have told earlier, we are looking at the same area from different positions. I can see here the different positions from where the same area is being looked, and it is considered as a single antenna, so that in the image you can find the synthesized antenna. It is all these A to G locations of the antenna will be considered as a single synthesized antenna, which will improve the resolution of the data received. And the radar layover is a characteristics of the radar image where elevated objects like a hill is being mapped from a side looking, where you will be able to see in the figure that the hill is marked as A, B and C, and B is the peak of the hill. And in the image you can see that the peak of the hill is being laid over the bottom A. So that is the layover, image layover, because of its height and the side looking. The A is falling behind A, B is falling behind A, so that the peak of the hill is falling behind. That is why it's called radar layover. And the radar shadowing is on the other side. If it is a gradual hill which has got a long slope, and the vertical slope on the other side, and near vertical slope on the other side, what will happen is there will be a foreshortening of A and B. A and B is a long distance in the natural hill, but in the image the distance will be shortened, which is called foreshortening. And on the other side there will be a shadowing of this long slope, so that the other slope may not be visible. Since the look angle is from the side of A and B, shadow will be towards C. So foreshortening and shadowing and layover are three characteristics that is seen in the radar images. You can see here foreshortening of this lower and the cone, volcanic cone. You can see the foreshortening of height on the northern side. It's an aerial image, aerial photograph on the right, and X-band image on the left. You can see the foreshortening of height on the top side, on the northern side, and also foreshortening along in the top images in the C and L band, where shadow on the other side, and foreshortening on the direction of slant. Yeah, that's happening. And you can here also see the shadow along the valleys, and for size small darker shades that gives depending upon the height and the position of the satellite. So some of the applications, SAR applications, synthetic aperture radar application, is the generation of digital elevation models. As we are able to identify height of objects, we will be able to generate digital elevation models. Land subsidence, continuous monitoring will help us to identify land subsidence. If there is some depression, some land has gone down, so that the height variations can be calculated, and subsidence monitoring can be done. Estimation of soil moisture content, that we have told, because of its penetrative capabilities and dielectric constant characteristic, we will be able to identify the soil moisture content. Biomass estimation can be done, as the height of the object is estimated. Canopy characteristics can be estimated by the reflection in the shorter bands, shorter wavelengths, and the bark reflection can be estimated. So all these deflection from the canopy and the trunk characteristics, moisture character, soil moisture characteristics, leaf moisture characteristics, etc., can be analyzed, and biomass can be estimated. Crop estimation can be done. Production forecasting can also be done with the help of radar, synthetic aperture radar application. Flood control can be done, as we have told earlier. It is possible to monitor even in the cloudy conditions and rainy conditions, and uh, in the flood possibility, or the monsoon time where there is flood possibility, we will be able to monitor the area, where, since we have got the digital elevation models generated from the SAR technology, and also as we have data of water bodies presently available, and as we can develop models where which are the areas that is going to be flooded, when there is a particular amount of runoff can be estimated, particular amount of rain, if it is there, this much will be the amount of runoff, and flood possibilities, and which are the areas that will be flooding. So flood estimation, flood control can also be done. Oil spill monitoring can be done, as we can directly map the oil spill. Detect oil spill can be detected directly with the help of radar, and even thickness of oil can also be calculated. So with the help of stereo pair DEM generation is possible. Parallax of pair of SAR imagery is used to generate digital elevation models. Interferometric SAR can also be done between two. We use two phase difference to build interferograms and fringe maps, so that from the fringe map, SAR images were used to estimate the surface height. And subsidence monitoring, as I've told, the technical, this height difference will be can be utilized if it is continuously monitored, or from differential interferometric SAR. So it's interferometry, differential interferometry can be utilized to identify millimeter level accuracy of land movements. So millimeter level changes can be monitored in the differential interferometric SAR applications. It can help predicting hazards such as mining, landslides, and land creeping. All these things can be monitored with the help of SAR data. Soil moisture, as we have told earlier, dielectric constant is calculated with the SCAR backscattering. Soil moisture content accuracy is estimated result depend on the SAR wavelength and polarization. So dielectric constant, it's useful in irrigation monitoring and as well as environmental monitoring. Biomass estimation, as we have told, it's possible. The SAR polarimetry is used. The polarization state of receiving and transmitting channels is employed to measure the differences in backscatter due to orientation, shape, and material composition. So polarimetry is used in biomass estimation. Interferometry along with polarimetry is used. So that interferometry gives the size, height, and all other aspects. Polarimetry gives characteristics. And combining these two technologies, the vegetation properties such as height, biomass can be determined. So polarimetry and interferometry is used in tandem to identify the biomass of that area. Crop estimation, it is used to monitor plant growth, estimate plants biomass, and total production of food, and it can forecast. Crop producing models can be developed with the plant growth, and the yield can be estimated. Flood control, as we have told earlier, flood mapping, as it's independent of seasons, we can map anytime you get the overlay with the DEM. Flood area can be mapped, movement can be delineated, affected areas can be mapped, possible areas can be identified. Monitoring of oil sills, the SAR data is cloud dependent, independent, and so oil cover surface is clearly displayed in SAR. So we can directly mark it out, and even the thickness of soil layer may also be obtained from SAR data. With multi-temporal data available, the source of pollution can also be discovered. With the multi-temporal data, source of pollution can also be discovered. So some sources of microwave data is from advanced microwave scanning radiometer, and the site is given the tropical rainfall measuring machine, and the site we will be having microwave data available in these sites. So the other technology is the shuttle radar topographic mission, which is again another technology which has got two antennas on board, and that is the longest objects that is being mounted in the satellite. And the introduction, instruments, elevation, how elevations data generated, process involved, and data details is being discussed in this session. And the shuttle radar topographic mission is launched to build a digital elevation model or the global data set of land elevations. And it has got two antennas basically payloads carry in the shuttle endeavor, and the launching was done in 2000 February, and it's in the altitude to 33 kilometers with 59-degree inclination, and the mission was completed in 11 days. It has got two antennas, that is the main advantage of this technology, that is basically single pass interferometry was used in SRTM. Single pass interferometry means it has got two antennas, so single pass itself it gets two interferograms can be generated because it gets two signals in two antennas. So radar on board on the space shuttle was used to collect images of the land surface. That is sent by National Geospatial Intelligence Agency and NASA. And the signal was sent from one antenna, and radar returns were recorded in two antennas at a known distance, and the radar images were interpreted to generate high resolution elevation data at near global scale. So it can generate elevation data at the global level. So near global coverage is done with the help of SRTM, which is extensive application the system sciences, hydrology, land use planning, communication system, designing, and military purposes. So SRTM was heavily used in all these areas, and it finds extensive applications in hydrology, land use planning, system sciences applications. So all these areas, basically the digital elevation model is highly useful in all these area of applications. So its advantages can be explained like this: it can operate day and night, it can operate in bad weather. By using spaceborne radar systems for mapping, the accessibility to issues are eliminated. So these are the radar system advantages, and you can see the figure with the mast and the antenna, two antennas, one along the along the shuttle, and the other one is at the end of the mast. So you can see main antenna located way of the space shuttle, and mast, which is a long outboard antenna at the space shuttle. Outboard antenna is connected at the end of the mast. So this is the longest object that is available in space, and the main instruments are the in the main antenna consists of C-band radar antenna and X-band radar antenna. So used to send radar signals and to receive the radar return. Main antenna consists of two antennas to work to two different wavelengths, and it can carry information at two different bands, C-band radar and X-band radar informations. Transmit in C-band radar signal wavelength of 5.6 centimeters, and the swath width of the C-band antenna is 225 kilometers. The C-band antenna was used to scan about 80% of the land surface, and it covers almost all the 80% of Earth, and have developed a elevation model for all these area of the 80% of the Earth, and it's 60 degree north and 56 degree south. In between 60 degree north and 56 degree south, entire area is being mapped, and 3D models has been generated. And X-band radar antenna transmit and receive X-band signals at the weight 3 centimeters. So 5.6 centimeters covers a larger area of the globe, and 3.3 centimeters band 3 signals can cover less area, and using shorter wavelengths, high resolution was achieved. So resolution can be improved by shorter wavelength in the case of 3 centimeters, but it cannot cover the entire area. But 5.6 centimeter covers 80%, almost 80% of the global area. And we can see here, as we have told earlier, the mast is used to maintain a baseline between two antennas. Length of the mast is 60 meter, and it is inclined at a 45 degree from vertical. So it provides a baseline distance between the main antenna and the outboard antenna, and it is a longest or largest rigid structure ever flown in space. And you can see that in the case of outboard antenna, it is connected at the end of the mast, as we have told, and no signal was transmitted from the outbound antenna. Only the antenna along the shuttle is transmitting signals, and the signal reflected is being received. Backscatter is received on both the antennas, onboard antenna and outboard antenna, and its C-band contains two antenna, contains C-band and X-band antennas. C-band wavelength is 5.6 centimeter, X-band wavelength is 3 centimeters. So data for the global, as we have told earlier, is being collected in the 5.6 centimeter. 80% of the global area is covered, and elevation data has been generated, whereas in the case of 3 centimeter, better resolution would be achieved with a less coverage area. And the radar interferometry in the case of SRTM, since the elevation data is generated with the radar interferometry, as we have told earlier, the radar interferometry is being done with the help of the phase difference or with the help of fringe map, and the signal from a single source, main antenna, radar returns were recorded at two antennas. These images recorded at two antennas were used to generate interferograms, and phase difference is estimated from interferograms. Phase difference or the fringe maps have been generated from the interferograms, and it's used to calculate the slant range. The slant range is calculated from the phase difference. HCCL2, height of the object, as we have told earlier, is the height of the satellite or the antenna minus the radar pulse S1 along the near range, and cos of theta, that is the look angle, cos of look angle. So HCC altitude, orbit S1 is the slant range to the nearest land, nearest range, and theta is the look angle. So the processes involved in the SRTM is the radar holograms, that will be the initial products, and from the radar holograms we need to build the radar images. From the radar images we need to develop the interferograms. From the interferograms you need to build the digital elevation models. So holograms, we need to build, we'll have to process the image to build radar images. From there, the processed image can be used to develop the interprograms. Once the interprograms is developed, we can identify the elevation of the objects, and then with the help of the elevation of the objects, we can build the DEMs, or the digital elevation models. The coverage and processing, we have told a bit earlier. Elevation data from C band and X band. So near global coverage was attained in the case of C band, and we have told this 60 degree north to 56 degrees south. It is covering then almost 80% of the globe, and elevation models have been generated. Smaller wavelength in the case of X band helped to have better resolution, and digital elevation data was generated using radar interferometry. Interferometry was a technique used, and the process was discussed just in the previous slide. And the elevation data was processed to fill small voids. You will have voids in the elevation data. Some corrections need to be done. Remove spikes, delineate or flatten the water body, and to improve the coastlines. All these things were done, and final products are ready, and it's downloadable free in the 30-meter resolution and 90-meter resolution. You can see the coverage area of C band, which is almost 80% of the globe, and the coverage area of X band, which is only part of the globe, not as the coverage of the case of C band. So resolution and data formats can see the data can be downloaded from the USGS Earth Explorer site. 1 arc second data, approximately 30-meter resolution for now, and the globe is available. 3 arcs data, which is 90 meter for 80% of the globe, and SRTM elevation data is available in 2 formats, basically DTED, digital terrain elevation data, and bill, band interleaved by line format. So bill format and DTED format data is available regularly. Spaced grids is the digital terrain elevation data, which is the raster format, and elevation data in binary format for regular grids in the case of band interleaved line. So publicly available SRTM DEM is georeference with WGS 84 datum. So basically it's WGS 84 datum based DEM is available publicly, and accuracy is 60 meter accuracy in the absolute elevation, and 10 meter for the case of relative elevation. So if you look at an object, its elevation, absolute elevation will be 60 meter, there will be a variation of 16 meter. But if you are looking at 2 different objects, the relative elevation difference will be around 10 meter, and it will be in the 90% of confidence level when in the accuracy assessment. Thank you. That's for now in the case of micro remote sensing.